Hello all. The assignment given to me is regarding Excel sheet, which is supposed to give the predictions based on the given data. So the data was in numbers and regular numbers. So what I thought was I will go with the regression, and I started with the first Excel sheet, tried to convert. I was able to do some of it in Excel, but then I thought, let me do the same in the Python, and uh, I I used three regression models into this Python. One was a linear regression, then there was a decision tree regression, and then the random forest regression. So the whole idea is just to first to upload the data, and this is the command for uploading the data. You create a data frame, and then you just check the information about the Excel sheet. And after checking the information, whether the whole thing is in a perfect shape, there is no not null value, and everything is in which format it is in, you get a brief information. Then you write another command, which is describe. So with the help of this describe, you dig a little bit deeper, and then you get to know further what sort of data is there into that describe method. Let me show it to you. If you so this is which is showing is that you have non-null values. The total number of count of the Excel sheet is 9568 for every variable. Now these AT, V, AP, R, RH, PE, all these variables mean that they are basically variables which are being used in that power plant, and this is the outcome variable. So our input variables are this, and output variable is PE. And if you have a simple linear regression problem, then you can probably use a statement y is equal to a plus mx, y is equal to mx plus b. But if you have because we have many inputs over here, so you'll be using multiple regression, right? So the multiple regression means we'll be using these variables to check which one is a better combination, and it will increase the output p. Now, having said that, let me just move ahead with the code. What I initially did was uh, we have to basically check these variables to see how they are correlated with each other. If there's a good correlation, that means uh, when I say good correlation, that means correlation vis-a-vis output variable. So if there is a good correlation with the output variable, that means those features can be taken. And if there's not, we will not put them on the priority. So we can check these correlations with the help of heat map. So if I see heat map, so this is the heat map. So heat map, on the one hand, you have 1, and other hand you have -1. So you check uh, how these are correlated with each other. So if we see uh, on this heat map ATV AP, these are the input variables, and the output variable is PE. So we can see from this color combination, these, because these are, we can see that AT and V are highly correlated with PE. Similarly, AP and RH, they are not that much highly correlated with the PE variable. If we want to check that how these variables are interacting with each other, not with output variable, how interacting means how they are correlated with each other. So we can do this bivariate graph. So what it shows is basically, now it shows on this, you see this ATV, AP, RH, PE. Similarly on this axis, we have this thing. Now we can see from this graph that uh, AT and V, they are highly correlated with each other. From the shape, we can see they are highly correlated with each other. So this can be a problem. We call it as a multicollinearity. So how can we avoid multicollinearity if this is not good? So probably we can take whichever in these variables is highly related to output variable, we can take that. So in this case, we will take 80 because it has got a value more. So we'll take it from there, and then probably we can proceed ahead. So these graphs are basically for our understanding and for our consumption to see how these variables are uh, correlated vis-a-vis the output variable and vis-a-vis how they are correlated with each other. So these graphs can help us understanding this thing. Now, with this background, I will now explain this functioning of this thing now. So what happens is, I am taking basically three questions and I am trying to answer this thing. First, I'll start my program with exploring my data. My data is correct or not? Is it having any non-null values? Anything like that. So that is called exploring your data. So once you have explored your data, you start with importing these all pandas as PD, numpy as NP, matplotlib, seaborn. These will be used in as we progress in this program. Similarly, as I told you, I'll be taking decision tree regressor, random forest. So you have to take them from their own respective classes. So once you start this thing, you load your Excel sheet which has been given to you, and then you check. You just have overview of what your data is about, right? And how it is, I mean, what is the size, minimum size, maximum size? These queries can give you that detail. After you get the brief detail, now you dig deep further into it, which is you just check that heat map for the correlation. So you give that fig size. Fig size means the size of the squares which is going to be shown on the heat map. Then you also have this bivariate di diagonal bivariate graph, which gives you uh, understanding of multicollinearity. If ever your variables have multicollinearity, this thing will help you. Now you are now going further after you have explored the data. Now, what is happening is you are now trying to develop the model. So what does that mean? That means you will now use different models. Like I told you, you will be using linear regression, decision tree, and random forest. But for that, you have features. So what we'll be doing essentially is we'll be taking different permutations and combinations of the feature, and then we'll be giving it to the models and see how the models are coming out with the values. So in the first, what we'll be taking is 80. 80 is one of those values. This 80 is one value, V is another value, AP is another value, which has been given to us in the Excel sheet. So we'll be taking in the first, what I've created is, because I want a proper outcome to be seen in the end. So I have created this feature set. So set means in the first we have taken only 80, another we have taken 80 and V, third I have taken 80 V and RH, and fourth I have taken all the variables, which are the basically input variables. So I am now taking in the first, and then Y is a outcome variable, which is P. From this diagram, we can see P, PE. This is what we are trying to see. So Y is the outcome variable. Now, again, this is how to furnish the outcome. So it's just the ornamenting the outcome. So what I have done is I have created a result, and in the result we have metrics, model. These are empty sets, and we'll be putting values inside it as in when we come across. So just rush forward. We see what happens is, now that we have created the features, we'll be now try to train the model. So basically what happens is we normally do 80-20. We take the 80% of the data and we train the model. And once we have trained the model on that 80% of the data, which has been given to us now, and we are sure that, okay, the mathematical model has been arrived at. Now, on the same mathematical model, we'll take the remaining chunk of 20% of the given data into that model and see whether it is giving the correct outcome or not. So that is called testing. So for that, what we do is we have this x train, comma x test, y train, y test, and this is train test split. So we are splitting. 0.2 means 20% is a test size, and we give this into 20% of this thing. Here I have created a evaluate model. I have created a model, and I am just putting these details into it. And first I have taken is linear regression, and in the linear regression I am giving X train and Y train. We are basically training the linear regression model, and then we have Y predict is the outcome. LR predict, we are giving X test, and it is giving a Y predict. Now again, as I told you, result is empty, and we are just entering the details. The first line is RMSE, R square, ME. What are these? Basically, what I am doing is I am trying to uh, see the performance of these models, and I am evaluating them on RMSE. RMSE means root mean square error, then R square, then MAE means mean absolute error. So I am trying to evaluate these models, linear regression, decision tree, and random forest on these parameters. So initially this is a header, and then I am doing is basically I am calling this linear regression dot extend, and I am now putting these things, square root, which is when I'm trying to calculate square root is mean square error, and I'm putting y test and y predict, and then r square, this is the second parameter, and then mean absolute error, which is the third parameter. So on these three parameters, I am checking linear regression. Similarly, on the decision tree, I'll be checking mean square error, R square, and mean absolute error on the decision tree. Similarly, I'll be checking these things. The interesting thing is, once I have written this code, now what I'll do is I will now enumerate them, as in I'll be calling the model, evaluate model, which has been already defined here, this one, and I'll be putting the details into it. So once I put the details and the features have been mentioned here. Here they have been mentioned. The first row is simple, one variable. The second row has got two variables. Third has got three, four is four. So one by one, these features will be put into this thing, and the results will be now in the data frame, right? So once I have done this thing, now it has created a data frame. Now I will pivot the whole data frame in order to see the desired format. Once it has been done, and I will display the data format. Now it will be like this. Now before I dig deep into these three parameters, I just wanted to inform that MAE, which is called mean absolute error, this is, if ideally the lower MAE, the better for us in any model, right? And a root mean square error, the lower RMSE is, the better is for our model. And R square, the higher it is, the better is for our model, right? So with this information in mind, we will now check every model, because we have got the output linear regression model 1, linear regression model 2, linear regression model 3, linear regression model 4. Similarly, for decision tree, we have got model 1, decision tree model 2, decision tree model 3, model 4. Similarly, random forest model 1, model 2, model 3, and model 4. Now, what we will do is we'll try to check, because I told you at the start, mean absolute error, lower it is, better it is for us, right? So in this linear regression, the MAE, uh, if we will go for model 1, MAE is 4.17. For model 2 is 3.85. For model 3 in linear regression, it is 3.57. And for model 4 is 3.56. So that means if I have to check on the linear regression, I can easily conclude that the model 4 has got the MAE lowest out of all the four values. Similarly, if I have to check MAE value for decision tree, and for decision tree, I see the MAE is 4.6, and similarly for model 2 is 3.16, and again model 3 has got 3.217, and model 4 has got 3.11. So if I say, I can comfortably say that decision tree in the model 4 has got the lowest MAE value. Similarly, if I go for random forest, if I check MAE 4.44, and random forest for model 2 is 2.60, for model 3 is 2.53, and for model 4 is 2.34. So I can safely assume in random forest, model 4 has got the lowest uh, MA value. Now, these were the model values. These were the MA values for these three models. But if now I compare all these models simultaneously, linear model, decision tree, and random forest, which amongst them has the lowest MAE, I can easily see that model 4 in the random forest has got lowest value, which is 2.43. So here model 4 is the winner in case of MAE. Similarly, if I choose RMSE in model 1, model 2, model 3, model 4 of linear regression, what I see is I have got model 4 as the lowest value, right? Because it says 5.27, 4.84, 4.454. So model 4 has got the lowest value. Similarly, for decision tree, if I check uh, here, M2 has got, model 2 has got 4.4, which is the lowest, right? And now if I check uh, random forest has got model 4 has got the lowest one, right? Now, if I amongst all these chosen RMSCs, if I compare them, now it's a sort of a round robin league. Initially, for their own groupings, they came up with their lowest. Now, amongst all those chosen one, if I come across again, I'll see model 4 has got the lowest value. Similarly, for R2, I just mentioned at the start that R2 has to have highest value. What I realize is that model 4 has got the highest value, because if I see model 4 0.96, here model 2 has got 0.95, here it's got 888, here it's got 0.92, here 0.92, here 0.93, here 0.87, 0.93, 0.93, 0.90, and 0.91. So if we see the highest one has got model 4. So we can easily now conclude that model 4 is the clear winner on these performance parameters in mean absolute error, in root mean square error, and R square. Model 4 of the random forest regression is the winner, and it has clearly uh, you know mm, allowed us to come at the conclusion that this will be having the most success. When I say success, that means if I say 96, that means 96%, right? So we can now see that, okay, this is the best model among all the seen by doing the comparative study. So that's it from my side. See you soon. Thank you.